Okay. All right. So we're gonna continue on with electrostatics today. Before we start that, so we'll go over the homework questions. So this is homework. This is homework 3. It's on vector surface integrals and the divergence theorem, vector line integrals, and the Stokes theorem. So yeah, this homework is more difficult than your last homeworks. It's also fairly long, though it is 100 points. There's what, six questions, but each of the questions has multiple parts. So let's go over any questions that you might have. Justine, I think we can start with you. Mm-hmm. 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 Ah, yes, absolutely. Let me see if one of the problems that we actually did in the homework related to that one. Yes, this is probably the closest example, right? So in this case, you're given a vector field. Okay, what that vector field is not important, but you're integrating over a function. Okay, now when you have line integrals like this, I suggest following the same approach for all the line integrals, because it will get you there every time. And here's what the approach is. So you want to find the integral of a dot dl from a single point to another point. So in this example, the line integral was from the origin up to 1, 1. All right, and so of course, if you want to find a dot dl, the integral of it, you have to, let's first find out what dl is, and then we'll figure out what a dot dl is. So the key thing here is that you have to define what dl is. Now, you have this relationship y equals x squared. All right, and if you take the derivative of both sides of that, you have dy is equal to 2x dx. Right? Everyone with me so far on that? Nod, shake your head. Okay. Okay, this is the key here. All right, you have a function y in terms of x, right? And then you have dy is equal to 2 dx. Now you have to put dl in those terms. All right, so what we're doing here is we're saying dl is equal to dx times x hat plus dy times y hat. This is the definition of what dl is in Cartesian coordinates. But what we're doing is here we are substituting. This is the key trick, secret sauce, if you will. We are substituting so that everything is in terms of x. So you just have dx times x hat plus 2x dx times y hat. And we used these relationships here to do that. Now, why would we want to put everything in terms of x? Because this is a line integral. It's a single integral, right? So you want to integrate with respect to a single variable. If you can put everything in terms of one variable, that's the way you do this problem. All right, so that's why we put dl in terms of x. And we're also going to put a, the vector field a, also in terms of x. Y times y hat. Well, y is equal to x squared, so we can put that in terms of, we can put everything in terms of a single variable. Right, so integral of a dot dl is equal to y times y hat dotted with this dl vector. Okay. And let's see, what do we have here? So you dot these two, you dot the y components together, you get 2x times y, but then y is equal to x squared, so you end up getting 2x cubed. And the x component, remember, there's no x component to the vector field A, so that one cancels out. But ultimately, in the end, you have everything in terms of x, and it just simplifies to a regular integral, and you integrate that, and you get 1/2. Yeah, we went over this problem in, we went over this problem, I think 2 lectures earlier. Yes. Yeah, it should be on there. Oh, am I recording it now? Yeah, I'm recording it now too. Everything's being recorded. Yeah. Justine, does that help you then? Yes. So that you brought up a very good question. When you put the trick here was to put everything in terms of a single variable, right? So now when you the limits of integration is with respect to x. So you can see here is that as we go from this point to this point, x is going from 0 to 1. Because we put everything in terms of x, so we can integrate with respect to the limits of x. If we put everything in terms of y, which is also we could have put everything in terms of y, then we would integrate from y is equal to 0 to whatever, this point, the y coordinate of this point to the y coordinate of this point. Yes. It's easier if you put everything in terms of one variable. Yeah, I would suggest doing everything in terms of a single variable. You're asked to find the line integral. So, uh, so that's f dot dl that you're looking for here. I'm sorry, this one, x cubed. This x cubed. This is just the value of the vector field. This tells you how strong the vector field is, but you're integrating along this line, y equals 3x squared. Yeah. So I would follow the similar approach as what I did in this problem. So in this problem, you're given a vector field. It's a simpler one, but it's still, it's basically the same type of problem. This is the vector field that you're given, right? And the first step you do is, you're going to find the integral of a dot dl. So the first step you do is find dl. And so we went through and just found dl here. And then you find a dot dl. And when you integrate that with respect to a single variable. We put dl in terms of a single variable. Ultimately, we put a also in terms of a single variable because we substituted for y. So this integral ends up being everything in terms of x. And we're integrating from x equals 0 to x equals 1. Oh yeah, you definitely do, because the values for the vector field, this is the vector field, y times y hat. You are taking the dot product of that with dl. So that's where the values of the vector field come into play. If this is a three-dimensional problem, then yes, you would have the z coordinate as well. But in this example, this is just a two-dimensional problem, and in fact, problem 1 is also a two-dimensional problem. Now, problem 2 is, I would say that I'm giving you a hint here, because this is a problem that we've done something similar in class, but we haven't quite done the exact same problem in class. This is a three-dimensional line integral, and instead of putting everything in terms of x, you're actually going to put everything in terms of u, because you are going to take the line integral along a helix. Do you guys know what a helix looks like? It looks like a twisty line in three-dimensional space. What's that? Tweezer? I'll show you what a helix looks like. This is something like that. Twisty line. So this is a three-dimensional line, right? The example problem that I just showed you was a two-dimensional line. This is a three-dimensional line, and we're going to take a line integral along that. So that's a slightly more challenging problem, but you'll see that if you put everything in terms of u, this will be fairly, it'll just end up being a basic integral again.
Okay, do we have to change it to
No, this one is given to you in Cartesian coordinates. You can work in the Cartesian coordinate system the whole time. All right, more questions. All right, so let me just give you the preview of it then. Problem 3 is the divergence theorem. So the divergence theorem, what does the divergence theorem tell us? Yes, it's a way to calculate the total flux on the surface, right? The divergence theorem tells us that two ways to calculate the total surface flux. One is to calculate the surface integral of an enclosed surface, of a closed surface, and the other way is to calculate the volume integral of the divergence within the surface. So in this, in problem 9a, you're going to calculate the flux using a surface integral, and there are 6 sides of the cube, so you're going to have to do 6 surface integrals here. And then you're going to do the same calculation by using the triple integral of the divergence. And your problems in A and B should match. Oh, I just gave you the answer to part C. Okay, in number 4, now we're again doing another divergence theorem problem, but we're doing it in spherical coordinates instead of Cartesian coordinates. Okay, similarly, number 5 and number 6 are both on the Stokes theorem. What does the Stokes theorem tell us? We just talked about the divergence theorem. So what's the Stokes theorem? It's for circulation. 2 ways to calculate circulation around a two-dimensional surface. And what are the 2 ways you can do that? Yeah. What are the 2 ways you can calculate the circulation according to the Stokes theorem? The line integral around the contour, that's one of them. And what was the other one? The surface integral of the curl. That's right. Right, so this is also 2 ways to solve the same problem. So in part A, you're going to use the circulation. In part B, you're going to use the integral of the curl, and both of the answers should match. Similarly in 5. Okay, these are the reason I'm giving you similar types of problems just in different coordinate systems is so that you can get practice in different coordinate systems. And in these problems, you're going to do a lot of surface integrals and a lot of volume integrals, and so it'll just give you the practice that you need to feel comfortable with this kind of stuff. All right. So, if you have questions between now and Monday, please let me know. We can always. I may not be here on Friday, but tomorrow I'll be here. If you have any questions, you can email me. Friday and the weekend, also, if you have questions, email me. I'll get back to you as soon as I can. And Monday, I have office hours from 3 to 5, and I don't believe I have any appointments yet. So you can come in during office hours for help too. Really? I'll tell you what. I can delay the homework till Wednesday, but the following homework I will not be able to delay because of the upcoming test. That's right. So the next homework will probably be due Monday. Yeah. So I don't mind delaying the due date of this homework if it gives you extra time, but I do need to get the next homework going probably on Monday, probably by Monday to assign it and for you to get started. And if we can make that next homework due the following Monday, then Wednesday you'll have a chance to review it, right, before the test. I just want you to get feedback on the homework before the exam. You know, whether it's asking questions in class, whether it's having some of the homeworks back and graded, whatnot. Okay. So yeah, that's fine. If you guys need a couple extra days on this and turning in this assignment, it's okay. All right. Any other questions, concerns, things you want to talk about? All right. Good. So let's quickly recap what we did last time, and then we'll continue on to Coulomb's law. So today will be mainly about Coulomb's law, and if we're lucky, we'll get into potentials. Coulomb's law and Gauss's law we'll cover today. All right, quick recap of last time. So let's just roll through this from the beginning here. We started the electrostatics module last time. We talked about some basic rules of electrostatics, meaning like the Maxwell's equations. All right, there are 4 Maxwell's equations: Gauss's law, Faraday's law of induction, Gauss's law for magnetism, and Ampere's circuit law. In statics, the definition of statics was that time derivatives go to 0. So you're at steady state. So steady state means all the time derivatives go to 0. d dt is equal to 0. So this ends up getting rid of the dB dt and dd dt terms. And now what happens is that the electrical and magnetic field are no longer coupled to each other. Notice that this equation has an electric and a magnetic field. This equation has a magnetic field and then an electric field here. These equations 2 and 4 couple magnetic and electric fields together, but they're only coupled in non-steady state situations. If you're in steady state and these time derivatives go to 0, then you have a set of 2 equations that describes electric fields and a set of 2 equations that describes magnetic fields. So these fields can then act and exist independently of one another. All right, so we looked at these fields and we wanted to develop an intuition of what these equations were. All right. Del dot D is equal to rho V. The intuition behind that is that whenever you have a charge, rho V, the field lines radiate away from that charge. Del dot D is divergence. Remember, divergence describes how much, the higher divergence is, the more the flux lines radiate away from that point. So wherever you have a charge, there's going to be field lines radiating away from it. They radiate away from positive charge, and they radiate towards a negative charge. Field lines go away from a positive charge, and field lines go towards a negative charge. That's the Maxwell's equations number 1. That is called Gauss's law. Maxwell equation number 2, del cross E equals 0. This means that the electric field is irrotational. It does not, you won't, in statics, you won't find electric fields that go around in a loop. Magnetic fields you can, but not electric fields. Electric fields always go from positive to negative. They point from positive charge to negative charge. In every single example you'll see in electrostatics, that's what happens. You will never find an electric field going around in a circle like this. We talked about the Feck and Ved rule. The main thing here was the force is equal to EQ. If you have an electric field and you have a charge in that electric field, the electric field essentially pushes that charge. The force is equal to the electric field times the charge. And the way you think about an electric field, you have you apply voltage between two plates of a capacitor. You get positive charge on one end, negative charge on one end. That generates a uniform electric field between the two plates. So that's your electric field E, and this Q is just the charge, the amount of charge that this little particle has. The force is equal to E times Q. Notice that it's in the direction of E. This positive charge will be positive charges will move in the direction of the electric field. Negative charges will move in the direction opposite the electric field. This makes sense because remember, like charges repel. So these are all the positive charges here. This Q is going from positive to negative charge. We talked about the differential and integral forms of the electrostatics equations. This was del dot D is equal to rho V, del cross E is equal to 0. This was the integral form of it. This is a triple integral of the divergence. You can also convert this into a surface integral. We'll talk about more of that today using the divergence theorem. Del cross E is equal to 0. The surface integral of this is actually equal to the line integral of the electric field around a contour. That is applying Stokes' theorem. D and E are related by this factor epsilon. D is equal to epsilon E plus the polarization. Now, in a lot of materials, we can just ignore this polarization, so it's D is equal to epsilon E. They're linearly related to each other. E is the electric field intensity in volts per meter, and D is the electric displacement in coulombs per meter squared. D is called electric displacement or electric flux density. I'll go into a little bit more detail of that when we start talking about dielectric materials, but it describes the displacement effects of an electric field on charges in a dielectric material. In a nutshell, you know, like if you put an electric field over a dielectric material, these charges align to the electric field. That movement, that displacement of the charges, that displacement is what this D is. Notice that it has a units of coulombs per meter squared. All right, now we talked about different charge densities. There's a volumetric charge density, surface charge density, and line charge density. If you want to get the total charge, if you're given a volumetric charge density and you want to find the total charge, you have to take the triple integral of that. With a surface charge density, you take the double integral. And with a line charge density, you take a single integral to find the total charge. So the example that we ended off with in class last time was a charge density problem that was you're given a surface charge and you're asked to integrate that over a disk and find the total charge. So this example is with surface charge, but in the homeworks or in the exams, I would expect you to be able to figure out line and volumetric charges as well. So these problems are just, I would say they're basic integral type problems. All right, for today's topic, Coulomb's law, Gauss's law. Coulomb's law is something you may remember from physics. Like charges repel, opposite charges attract. Coulomb's law quantifies that. So the basic relation of Coulomb's law describes the electric field created by a single point charge. So let's assume we have a single point charge at the origin that has a charge Q. And we have an observation point. So let's say the charge is in the middle here, the observation point is here, this point P. So the electric field is going to be given by this equation. Let's look at what the different parts of the equation are. R hat. R hat is a direction vector. What does the hat mean? It's a unit vector. That's right. So whenever you have unit vectors, it's just intended to give you the direction. It gives you the direction of this electric field. And this term here gives you the magnitude of the electric field. Right? So let's look at the direction first. The direction is just It's pointed, the vector, direction vector is pointed from this charge to the observation point. Electric field lines point away from charges, right? So if this is a positive charge, the electric field lines are going to radiate away from that point in space. So it makes sense that the direction of that electric field is pointed in the r hat direction, because r hat points away from the center. It points away from the origin in spherical coordinates. R hat always points away from the origin. Yes, this is given in spherical coordinates. You notice a capital R there. So I think I understand where some of the confusion may come from. I've drawn x, y, and z here on the coordinate axis, right? But the electric field is given in spherical coordinates. Small r generally refers to cylindrical, right? So what direction is this vector pointing? It's pointing from the origin to the observation point. So imagine a vector connecting the two. That's your r vector. R hat is just the unit vector in that same direction. Okay, so this part that I'm circling here with the mouse right now, this is r, which encompasses the entire distance from Q to P. R hat is only a part of that. It has a length of 1. That's the unit vector here. So this is r hat, shown in red. All right, now the magnitude of it is equal to q times 4 pi epsilon r squared. So it's telling us is that the electric field, it's proportional to the amount of charge, which makes sense. The more charge you have, if I double the charge, I'm going to get twice the electric field. The more charges you have, the more electric field it generates. That makes sense. The denominator, 4 pi epsilon r squared, this r squared term is something interesting. It tells us that the electric field decays. The farther you go away from that point, the electric field decays as a function of 1 over r squared. So just to remind you all, the function 1 over x squared, let's say this is x and this is f of x. The function 1 over x squared looks something like this. Right? So it's telling us that the electric field drops quite rapidly the further you go away from the point. And the units for the electric field are given in volts per meter. And one more point I wanted to make is that there's a dielectric constant in there. I talked a little bit about that in the last lecture, but different materials have different dielectric constants. And you can look it up and look at this chart here. Vacuum has a relative let me mention the dielectric constant epsilon is equal to epsilon 0 times epsilon r. A fixed portion and a relative portion. The fixed portion is always 8.85 times 10 to the negative 12 farads per meter. The relative part depends on what material you're working in. So if you're in vacuum, if you're in space, then ER is equal to 1. If you're in air, the dielectric constant is also very close to 1. If you get in other materials, the dielectric constant changes. So the electric field is inversely proportional to the dielectric constant. The higher the dielectric constant is, the lower the electric field is going to be. And the units, again, is volts per meter. Now, the force at this observation point, if you know what the electric field is, if you know what E is, the force is just E times Q. That's Fec. And the force is given in newtons. All right, so let's do an example problem here. If you guys want to jot down this formula here, you can just copy that down in your notes, and then I'll switch the slides over, and we can do a simple Coulomb's law problem. So just jot down this Coulomb's law problem formula. Okay, does everyone have it down? Okay. All right, so let's try this problem. So let's say we have a proton. What is the electric field 2 nanometers away from the proton? And the second part of the question is, if we had a second proton at this location, what is the repulsive force? So I'm going to give you a hint or reminder on this problem. The charge of a proton is 1.6 times 10 to the negative 19 coulombs. Again, the charge of a proton is 1.6 times 10 to the negative 19 coulombs. I can just add that in here. Proton charge 1.6 times 10 to the negative 19 coulombs. All right, so everyone give this problem a shot. What's the electric field 2 nanometers away from the proton? This is in vacuum, yes. E epsilon 0 is 8.85 times 10 to the negative. Epsilon, the dielectric constant. Oh, do you have a different question? So there's the first part of the question is asking, there's a single proton located at the origin. What's the electric field 2 nanometers away? That's the permittivity. Epsilon is the permittivity, and that's 8.85 times 10 to the negative 12 farads per meter. All right. So what did you all get? What's that? 7 what? 0.719 volts per meter. What did I? 0.719 volts per meter. All right. I had gotten a different. Sorry. Let's look at this. 1.6 times 10 to the negative 19 is the charge, Q. 4 pi epsilon r squared. Oh, you forgot to square the r. Okay. Yes. 10 to the negative 18. That will do it. So this one, is this what folks got? Okay. Okay, good. Squaring the r is important. Now the second part of the question, if you had a second proton at this location, then what is the repulsive force on it? Right, so this is a situation where, let me just draw it. If a proton at the origin Then you have a second proton 2 nanometers away. So the way that we do this problem, it's obviously fairly simple, but just so you know, the first thing we're doing is we're finding, we find the electric field at the observation point. What is the observation point? The observation point is here. That's where that second proton exists. The second step, to find the force is equal to the electric field times the charge here. So whatever charge this happens to have. And this problem, the charge here is actually the same as the charge here. The force is equal to the electric field times the charge, 3.6 times 10 to the 8th volts per meter, times 1.6 times 10 to the negative 19 coulombs. And that gives you a force of 5.8 times 10 to the negative 11 newtons. 58 piconewtons of force. Sure. Would you add them together? No. I mean, that's a fair question. But the strategy that we're using here is that there's one of the protons is giving off an electric field. Well, in this problem, the two charges, there's one charge at the origin and another charge 2 nanometers away. I mean, we're putting them 2 nanometers apart. That's the distance between them. Question? Yeah, please go ahead. Sure? Okay. All right. All right, next is we want to, now that we've talked about what Coulomb's law is, we can generalize it. This more of a general form accounts for when Q is not at the origin. So suppose that charge was not in the on the origin, and suppose that the observation point also is not at the origin. So instead of having Q being real just in the middle here, Q is somewhere out in three-dimensional space. So this is the charge, and then this is the observation point, P. So the same thing can be done here. Coulomb's law tells us that the electric field vector points in the r hat direction, meaning it points from the charge towards the observation point. From the charge towards the observation point. So that's what this r hat vector points in. And then the magnitude, it depends on the distance between the 2 points. So when you're generalizing it, that's essentially what you're doing is you're saying that, oh, well, it doesn't matter if this is at the origin or not. Like the r hat vector, the electric field vector is going to point from the charge towards the observation point, from Q towards P. That's why you see A hat QP here. This is the unit vector that's pointing from Q to P, from the charge to the observation point. All right, and notice that this, the vector, not the unit vector part, but the vector QP, the vector going from Q to P is equal to R2 minus R1. So what is R2 and R1? R1 is a coordinate. It's a 3D coordinate of the charge, and R2 is the 3D coordinate of the observation point. You'll see when we do an example problem here. So R2 minus R1, that is the vector QP. right? So this, yeah, please go ahead. The first example, in the first example, the observation point was here, but the charge was at the origin. The key point was that the charge was at the origin. And in this, when we're generalizing Coulomb's law, we're saying, well, the charge doesn't have to be at the origin, and neither does the observation point. They could be anywhere in space. But these, this here is showing that R2 minus R1. R2 is a vector that points from the origin to P. R1 is a vector that points from the origin to Q. R2 minus R1 is the vector that points from Q to P. If you remember from our vector subtraction that we did in the vector math section, this this triangle tells us that this vector here is R2 minus R1. All right, and also think about this. Just forget the fact that this is in spherical coordinates and all this stuff, and just think that, okay, if you have a point in space, some point P and some point Q, if you subtract the difference, if you're finding the difference between those 2 points, that's the vector that goes from one point to the next. Right? You'll see. We'll do an example of this. So the direction of the electric field is in the QP direction, so it's a vector that points from Q to P, and it's a unit vector in that direction. Q on the numerator, just like before, and then on the denominator, 4 pi epsilon R2 minus R1 squared. This is the length of this vector squared. All right. Now, if you simplify that, you'll get this formula here. Y AQP. So this AQP, this vector here, so that's the unit vector of R2 minus R1. How do you calculate the unit vector of R2 minus R1? You just take R2 minus R1 and divide by the magnitude. This AQP is equal to R2 minus R1 divided by the magnitude of R2 minus R1. All right, so you already have a magnitude of R2 minus R1 here, so this becomes cubed instead of squared. So you have R2 minus R1 divided by the magnitude of R2 minus R1 cubed times Q divided by 4 pi epsilon. All right, so here's another example. To find the electric field intensity, find the electric field at negative 0.2, 0, and 2.3 due to a point charge of 5 nanocoulombs at point Q, 0.2, located at 0.2, 0.1, and negative 2.5 in air. So I would like everyone to try this. Just go ahead and copy down this formula here, because you'll be using this formula. R2 minus R1 divided by R1 minus R3 cubed, the magnitude's cubed, times Q over 4 pi epsilon. Yes. A scalar. Yes, absolutely. Yeah. So this electric field will be a vector quantity, as we'd expect. All right, so let's see if we can figure this out. So keep in mind, this is in Cartesian coordinates. Sure. Yep. All right. Uh, any thoughts here? All right. It will be a vector quantity. Yes. If anyone has the answer, how about come up and put it on here, share it with the class. Yeah. Why not? Let's do it. And it's no pressure. Don't have it right, we'll help out and get it right. This is also in vacuum. Yes.
You have to hold this one. Okay, that's the eraser. Cool. Okay, so that's the top part, and then you have bottom part is gonna be the magnitude. All right.
Yeah, it seems a little bit hard to write on. Yeah, it takes a little bit of getting used to.
Am I doing right so far?
Yeah, seems right. QP is 0.4, 0.1, -0.2. Is everyone else getting that too? The vector R2 minus R1 should be equal to 0.4, 0.1, -0.2. So the P, let's see, what was the observation point? Let's go back to the question. Which one was the observation point? charge at Q. So P is the observation point. So the vector should be P minus Q.
Okay, I did the opposite way. I did Q minus P. Okay.
-0.4.
So pretty much the signs are all switched for all of them? Okay. Okay, I got you. Where was it on?
Yeah.
What's 6? I believe 8. The answer gives you -12 or not? Oh, I mean the power. Okay. So, do you do the when you have the vector over the scalar, do you divide in each part of the vector over the scalar?
That's correct.
You can do that?
Each part of the vector.
That's the charge of the proton. Oh.
This one's actually telling you what the charge is.
Oh, okay.
So 5 nanocoulombs would be 5 times 10 to the 9.
Sure. And then calculations for this. Over here, so you have 0.4 divided by 0.096.
So others can help. I mean, if you've done the calculations already, you can.
The stuff down below is 44.94.
And for this, it's a bit all over the place, but we'll combine it at the end. So we get okay. Wait. Um, yeah. Oh, my bad. Actually, I don't calculate it that way.
My solution is on number 10 and But I could have done a calculation there too. Let me double check my work. Yeah, let me just double check. One eighty. Well, I believe you guys. Is this what everyone else got too? Confirmation, Democratic confirmation. Okay, so we'll go with that. I probably just made a typo myself. So Q is on the order of 1.6 times 10 to the negative 19, right? I'm sorry, in this case it's 5 times 10 to the negative 9. The epsilon is 8.5 times 10 to the negative 14. All right. Or 10 to the negative 12, sorry. Right? And you've divided this by, okay, 0.458 cubed. Okay, I just want to make sure you had cubed it. Okay, good. Good. All right, so these are, these problems are just math, lots of math. Any questions on this? All right. So just to recap the way that this problem was done, right? The first thing we had to do was to find observation point is P, and the charge is located at Q. So you have to find the vector QP. So the vector, I'll just zoom in here. The vector QP is equal to the coordinates of P minus the coordinates of Q, right? And this is what was found as 0.4, 0.1, and negative 0.2. Wait, was that correct? Didn't we have a negative sign there? Yeah, this should be a negative sign. This should be a negative sign. And then this should be a positive sign. All right, you subtract the coordinates of the two from P, the coordinates of P from the coordinates of Q. All right, just for everyone's knowledge, this is a positive sign here. All right, and the denominator here we have PQ, the magnitude of PQ cubed, right? So the way you find the magnitude is 0.4 squared plus 0.1 squared plus 0.2 squared and the square root of that. All right, so it's P minus Q over the magnitude of P minus Q cubed times the charge Q over 4 pi epsilon R. I'm sorry, 4 pi epsilon. Okay, so this is your charge, 5 times 10 to the negative 9, divided by 4 pi, and then here's your epsilon. Okay, notice that the result that we get is a vector quantity. Electric field should be a vector quantity. Where's the z coordinate here? Oh, yep, I see it. This is the z coordinate. This is the y coordinate. This is the x coordinate. You will need a calculator for these types of problems. You could even do them in MATLAB. In fact, yes. I had started on this, but I didn't check it over. But let me just show you how you would do this type of problem in MATLAB. I think you'll find this useful. So let's go over each one of these things. I think last time you all were saying that you needed larger fonts, so let me just change the font size real quick. Fonts, here we go. Make this 14. Okay. I can move this command window over to the right side here. There we go. All right. So the first point, we're declaring P, and the way you declare P is a vector. So it's negative 0.2 and 0 and negative 2.3. That's the location of P. That's the observation point. So let's just denote this observation point. And then this is where the charge is. Q is where the charge is located. All right. So Q is at 0.2, 0.1, and then negative 2.5. QP, that vector that we have to calculate, is just it should be P minus Q. Yep. So that vector QP is equal to P minus Q. This is the observation point. Observation point minus where the charge is located. All right. Remember that, because that's, I was rusty on it. I switched them around sometimes by mistake too. Observation point minus the point where the charge is at. All right, and then the electric field is equal to QP divided by the norm of QP to the power of 3. Remember, the norm is the magnitude, right? So we're basically doing this formula. The vector between them, so that's this QP, and divided by the magnitude of QP to the power of 3. So this is QP divided by the magnitude of QP. And then multiplied by 1.6 times 10 to the negative 19. That's where I had the mistake there. It's 5 nanocoulombs, right? 5 e to the negative 9 divided by 4 pi times 8.85 times 10 to the negative 12. And then I don't know if you noticed this, but I put, if I want to suppress the output, I put semicolons at the end of the line. And then if I want to print something out to the screen, I can just put the name of the variable, and I don't put a semicolon there. Let's do this one first. This return thing means just to end. I just want to run the code. Oh, there it is. Thank you. All right, so there's my electric field. Negative 186, negative 46. Let's see if these answers match here. Negative 186, 46, and then positive 93. Good. You're good. You can use MATLAB to check over your work if you like. Nah, small rounding errors I don't care about. Now let me show some other things you can do with MATLAB. Visualize, visualize, visualize. This first command here is a scatter plot. All right, and what this does, it plots the point P. And the second command here plots the point Q. The command is scatter 3, and it takes you have to put in the x coordinate, the y coordinate, and the z coordinate explicitly. So x comma y comma z. That's why we're putting in P with the parentheses 1 around it means the first element of this vector. So the element, the vector P contains the x, y, and z coordinate. So the first element of that vector contains the x coordinate, the second element of the vector contains the y coordinate, and the third element of the vector contains the z coordinate. The next command is hold on. Do you know what hold on means? Keeps the graph, right. Otherwise, next time you do a plot command, it'll delete the previous graph and create a new graph. If you want to plot more than a single point on the same graph, then you have to put this hold on command. Scatter 3. So this is plotting the point Q. The next command here plots a line. It plots a line between P and Q. So scatter 3 is for plotting points. Plot 3 is for plotting a line. So with plot 3, you have to give it a list of x coordinates, y coordinates, and z coordinates. So these are the two x coordinates, these are the two y coordinates, and these are the two z coordinates. Right, so if we run this, so once you turn the hold on, it remains on until you turn it off. I'm commenting that out. This axis comment helps you set the axis limits. You know, if you want to go from x from this value to this value. But a graph will, I mean, if you just plot things, it should auto-scale it appropriately. So, and you can see here that this is the point P, this is the point Q, and we've just drawn a line between them. Okay, nothing fancy. If you wanted to draw a vector, then you'd use the function quiver. Right, so if I did quiver, I think it was quiver 3. Do you guys remember the inputs to quiver? Well, that's if you want the vector to originate from 0, 0, 0. This time we want the vector to originate from the point P. So we're going to do P1. Exactly. Yeah. Okay. P2, P3. And then we have to put the magnitude of the vector. So we just calculated E, so it's going to be E1, E2, E3. So this will give us the magnitude of the electric field. All right. You can see the electric field is quite large, so the 2 points are actually just over here. 2 points appear like they're a single point because they're so close together because the distance between them is small compared to the magnitude of the electric field. This is a relatively large electric field. All right, so that's how you use MATLAB to plot the vectors. Quiver, sure. So this one plots the vector. That's the electric field vector. Now, another thing we could have done, instead of plotting the electric field vector, we could have just plotted the vector PQ. Right? If we did that, then or QP, sorry, we could plot this vector QP1, QP2, then QP3. What are we going to see now? What is this vector going to represent? The vector between the 2 points, exactly. Let's run this. It looks like the vector's pointed in the wrong direction here. Do we have the right magnitudes? QP, P1, P2. Oh, it should go from Q to P. Yeah, so this should be Q1, Q2, Q3. There you go. So this is the vector pointed from one point to the other. So the quiver 3 function, this is the starting point. So we want to start at where the charge is, and the field vector points from where the charge is to where the observation point is. So this is the vector. These are the three components of the vector, and this is the starting point. All right, good. No, this is just Coulomb's law. I'm teaching you some tricks to how to use MATLAB because I think these functions you'll actually find useful in other classes too. You may find it useful in your career too. Just doing basic plotting and vector manipulations in MATLAB is really useful to know. All right. So electric fields due to multiple point charges. Suppose we want to find the electric field due to multiple point charges. There's something called the principle of superposition. Does anyone remember what superposition is when we're talking about circuits from circuits 1? All right, what is it? Yeah.
There's like a combination
Mm-hmm.
going off. You don't want to do it. Something else is that.
Mm-hmm. Mm-hmm.
Turn one on, turn one off, the same thing.
Exactly. Yeah, right on, right on. So if you're doing circuit analysis and you have multiple voltage sources in there, let's say you have a circuit and you're trying to find the voltage at a certain node, but that circuit happens to have three other voltage sources is in there. You can take out two of the voltage sources, find the voltage that you're looking for, calculate the voltage that you're looking for with just one source active. Find the result. Then calculate the voltage with the second source active, and then with the third source active, and you add up the three results there to get your final voltage. The principle of superposition means that in a linear system, the sum of the total force or the total field or anything, in this case, the total field at any given point is the sum of the contributions from all the sources. So let me be more specific because that's a mouthful. In the case of electrostatics, let's say you have an observation point P. And this time, instead of a single charge that's away from it, you have a bunch of charges. So in this particular picture, we have 1, 2, 3, 4 charges. And all 4 of those charges are generating electric fields. So there's going to be 4 different electric field components at the observation point, P. And what we have to do is add up the contributions of all 4 of those points. This says Q sub I. Yeah. All right. Probably the best way to understand this is to actually do an example. Essentially what you're doing, okay, this equation is just telling you that you have to split this problem up into 4 individual problems. Okay, you're going to split it up into 4 parts. First, you're going to find the electric field at P due to this charge, and that's going to give you an electric field. Then you're going to find, then you're going to add to it the electric field contribution from this charge, and you're going to add the electric field contribution from this charge, and so on. We did this problem with a single charge. We just completed that. So there's going to be 4 problems like that, and you're going to add the results from each of the 4 parts to get the total electric field. It is part of linearity for circuits. So you can use the principle of superposition in circuits if your circuit is considered a linear system, and which, most of the time you can consider it a linear system. If you have resistors and capacitors, they're assumed to behave linearly. I'm sorry? It would. Yeah, these circuits that have resistors, capacitors, inductors, they behave as linear systems. So the principle of superposition does apply. All right. Now, I was thinking about doing this problem together. I mean, I feel like it's going to be pretty tedious, and it's not a it's not a particularly challenging problem. It's just a tedious problem to do. Do you all want to do this, or would you like to just go on to the next concept? Just go on. Okay. All right. Good. There will be a problem like this on your homework, and you can do it. You'll see. It's just it's kind of boring, actually. Here, I'll do it. Homework is supposed to be a little bit boring, you know. It's just getting practice. It's all about practice. You'll see the homework that's due, you know, that's supposed to be due on Monday, but I'm going to extend it for a couple days. It's just a lot of like drill and practice. Because whether you like it or not, even if it's boring, ultimately that's how you learn. Like in biology, have any of you taking a biology class? You did? So it's in a way it's miserable, right? You have to memorize so much stuff. So the way you learn in biology type classes is that you just sit and you just memorize all the information that's being given to you. In engineering, the way you learn is actually by doing problems. And the nice thing is, like, at least from my opinion, in engineering, you usually don't have to memorize stuff. You learn by doing, which I would much rather like do problems and problem sets and just use my brain and solve a puzzle than just read out of a book and just see how much my brain can remember. Because I can't remember anything. If you haven't found this out yet, you're going to know by the end of the semester, like, I have a terrible memory. Yeah, they'll tell you the same thing. I have a terrible memory. Yeah. But even with anything, this is why I didn't go into biology, because I didn't want to memorize anything. Okay. So next question is, so now we have an electric field due to charge distributions. This is in a way an extension of this problem. Okay, so let's say you have an observation point here, and you have a charge here, a charge here, a charge here, a charge here. These are discrete charges. Okay, a single proton, if you will. In real life, I mean, we don't arrange single protons in particular geometries, right? What we actually do is there are charge distributions. What is a charge distribution? Well, a simple charge distribution is just a parallel plate capacitor. Other charge distributions are the things we saw here. Let's say you have a distribution of charge within a volume, or you have a distribution of charge on a metal surface, or you have a line charge density along like a wire of some sort. So for these charge distributions, they're gonna contribute an electric field, right? A single charge, you imagine that the field vector, the electric field lines point away from that single charge. What do you think would happen if you have a charge distribution like this? What would the electric field lines from here look like? They point upwards, right? They point away from the charge. So a disk like this, if you have a disk that has a bunch of positive charges here like this, the electric field lines will actually point away from it like this. They'll also point away on this side too. And on the edges, they'll point away this way, because the field lines always point away from the charge. It's really like connect the dots. If you have a linear charge like this, what direction is the field vectors going to look like? Sorry? Yeah, they'll point away like this. Really important that we just develop a basic intuition. They just point away from the charge. away from positive charge and towards negative charge. These are the electric field lines, right? All right, what if we have a spherical ball of charge? Let's say we have a bunch of charges in a ball like this. What direction are the field lines going to point? Yeah, exactly. Yeah, kind of like the sun, exactly. Very similar to a single point charge. Sure. Yeah, let's say you have a group of negative charges. You have single or group negative charges like this. What would the field lines look like? They go towards it. Exactly. I mean, in a sense, this is the nutshell of electrostatics. Everything else is just math. Electric field lines point away from positive charges and towards negative charges. All right, so we are now going to calculate the electric fields due to charge distributions. We have a surface charge, a line charge, a volumetric charge. The way you do that is you have to do an integral. And this is the whole reason we were doing integrals in the last chapter, because you have to use those integrals now. So if we have a continuous distribution of charge, you can use integrals to find out the total electric field. They can be found as follows. dE is equal to A sub r. All right, this A sub r is the unit vector that's pointing away from one of the charges on the surface or volume. And this is rho v as the charge density, 4 pi epsilon r squared. So this is essentially, this is Coulomb's law, okay? What we're doing here is we are taking Coulomb's law and we're integrating it. Why are we doing that? Conceptually, what's going on? Let's say we have a disk of charge like this. All right, let's say our observation point is, right here. We have to find the contribution from this charge. We have to find the contribution from this charge, the contribution from this one. We have to find the contribution from all the charges on this disk. So when we're adding up the contributions of all the charges on that disk, that is the integration that's happening here. So if we were doing a disk and we were integrating all the charges here, notice that we are doing a double integral over the disk, and this rho s is the charge. Every single charge contributes an electric field. Coulomb's law tells us that every single charge on that surface contributes an electric field. So we are essentially adding up the contributions from that charge. Right, so that's why you do this double integral. If you have a volumetric charge density, you use the volume integral. If you have a linear charge density, you use a linear integral. So these problems can actually get a little bit tricky. Yeah. A charge of a certain volume. Yes, the volumetric charge density tells you the charges per unit volume. That's correct. So don't get scared away by this, but I'm going to start you off with a problem that's it's a little bit on the difficult side. It's not impossible, but it's a little bit on the difficult side. And what we can do is, I think we have 10 minutes, so we can go over how to do it. We can go through it step by step. Let's see if I can find it here. I'll walk you through it. You're asked to find the electric field intensity of an infinitely long straight line of charge with uniform density rho L, coulombs per meter. So this is a line charge density. So let's draw this problem out here. This line has a bunch of positive charges on it. And as we know, if you have a bunch of positive charges like this, the electric field lines point away from the charge. Okay, and the charge density is given as rho L, coulombs per meter. So how many integrals are we going to have to do to find the total electric field? Single, double, or triple? It's a line, right? It's just a single integral. So the charge density is equal to rho L coulombs per meter. All right, let's say our observation point is here. All right, the point is at some distance, say some distance A away from that line. All right, and just so you know, this is an infinitely long line. So we have to use, since we have a rho L, a linear charge density, we have to use this equation here. The electric field is equal to 1 over 4 pi epsilon integral of A sub r rho L over r squared times dl. All right, what are all these things? First of all, conceptually, what are we doing? Conceptually, we are saying that there is a point A here. All right, now I'm going to delete these field lines here so you can see the point I'm trying to make. Non-cluttered. So if you have this observation point here, this is A. All right, so what we're doing here is we are saying, okay, well, we have a charge here. This is a charge Q. And so Coulomb's law tells us that the electric field line due to this charge is going to point from here to here. All right, so this is, let's say this is Q1. This is going to be E1. The electric field due to Q1 points away from Q1, right? This is the observation point. How about Q2? What's going to be the electric field line due to Q2? Yeah, just imagine drawing a dotted line here like this. It's going to look kind of like this. E2. Now, how about Q3? It's going to go in this direction. Right, and if you keep on doing that pattern, you see you're going to get a bunch of vectors that look like this, right? So what we want to do is we want to find the sum of all those vectors. We want to add all these guys up. Add these up. And that's why we're integrating. Now, I want you to think about something here. Think about this in terms of geometry. What is the total field vector going to look like? Yes, Isaac's got it. This is a very important point here. This is the symmetry. Why, Isaac, why is the total vector, E total, is actually going to look like this? Here, let me draw it in a different color. The total electric field is going to go like this, E total. Why is it going to be in a straight line like that? Or exactly. Exactly. Good. So the point that Isaac is making here is that the z components of these vectors are going to end up canceling each other out. Why? Because, all right, let's delete this here. Let's delete these two here. So we had E2 and E3, right? They are they're symmetric. They're mirror images of each other. So E3 has a x component and a y component. So let's call this Y3. E2 has the same x component, and the y component is equal to negative Y3. It's equal and opposite. So the y components of these vectors, when you add up E2 and E3, the y components are going to cancel each other. And you're going to be left with just the sum of the x components. Does that make sense? So E2 and E3 are going to cancel each other. Similarly, if we have two other vectors like this, E4 and E5, their y components will cancel each other. The y components cancel, and you end up with an electric field that's just pointed in the x direction. So this will become important when we do this integral. All right, so the electric field is equal to 1 over 4 pi epsilon integral of AR times rho L R squared times DL. Okay, backing up again, what are we doing here? We are adding up integrating the electric field contributions, and we're integrating this with respect to L. So we're going along the z-axis here. So this dl is going to be dz. We're going to be integrating with respect to z. This is the general formula. And for this particular geometry, the dl is going to be dz. And our limits of integration are going to be from z equals negative infinity to infinity. Because this is an infinitely long line of charge. Everyone with me so far? All right. The electric field is equal to 1 over 4 pi epsilon integral from z equals negative infinity to infinity rho L over R squared times dl, or dz, sorry. So we have to figure out the different components of this integral. I think it's 10 minutes after 9. Then it may be better to pick this problem up next time, because there's quite a few things involved here. So let's leave this till next week, and I'll see you all Monday. Homework will be due on Wednesday, but I will probably assign it, give another homework set due on Monday. All right. Any questions before we end? Why is dl equal to dz? Good question. All right. When you're integrating in this particular question, you're doing a line integral, right? You have a line of charge, and you have to add up the contributions from each one of those charges along the line. So that's why, like, this line of charge is along the z-axis. So we have to add up the contributions of each one of these charges, Q1, Q2, Q3, along the z-axis. So we're going to be integrating along that axis. Hey, good. Great. Let me just close this up here, and then I'll answer your questions.